At first glance, the deep space missions of Pioneer 10 and Pioneer 11 seem to be perfect examples of engineering precision. Launched in the early 1970s, these spacecraft were designed to explore the outer solar system, and they did, sending back the first up-close images of Jupiter and Saturn. Then continuing their journey outward into interstellar space, but as they drifted farther from the sun, something strange began to happen. Scientists noticed a tiny but persistent acceleration pulling the spacecraft very slightly toward the sun, as if some invisible force were tugging at them. This unexpected behavior became known as the Pioneer Anomaly. The effect was small, an acceleration of about 8.74 x 10 meters per second squared. That's roughly the weight of a paperclip resting on your palm. And yet, in the world of space navigation, such deviations matter. The spacecraft weren't behaving exactly as our best models predicted. Gravity, planetary influences, solar pressure, everything had been accounted for. So, what was causing the anomaly? Let's take a step back. Tracking spacecraft in deep space involves incredibly precise measurements of radio signals sent back and forth between the probe and Earth. By analyzing the Doppler shift of these signals, how their frequency changes due to motion, scientists can determine how fast the spacecraft is moving and whether it's speeding up or slowing down. In the case of the Pioneer spacecraft, these signals revealed that they were slightly decelerating more than expected, or equivalently, being pulled sunward. Could this have been a sign of new physics? That was one of the early and most tantalizing questions. Some theorists wondered whether our understanding of gravity might be incomplete. Could there be a modification to Newton's laws at very large distances? Was dark matter exerting a subtle influence on the spacecraft? Could this be a hint of a fifth force, or a breakdown of Einstein's relativity in the far reaches of the solar system? Others speculated about exotic explanations like interactions with quantum vacuum energy or unaccounted for space-time curvature. After all, anomalies in science often lead to breakthroughs. Could this tiny drift rewrite the laws of physics? But before rewriting the textbooks, scientists turned to the more mundane, yet often correct, approach. Check the instruments. Was the spacecraft itself causing the drift? This line of inquiry led to a breakthrough. The Pioneer spacecraft were powered by radioisotope thermoelectric generators, RTGs, essentially nuclear batteries that produce heat, which is then converted into electricity. As it turns out, heat matters in space navigation. If the spacecraft emitted heat unevenly, say, more radiation in one direction than another, this could create a tiny thermal recoil force. Think of it like a very slow, steady push, much like how light from the sun produces solar radiation pressure, but coming from the spacecraft's own body. After extensive modeling, researchers concluded that the anomaly could indeed be explained by asymmetric heat radiation. Some of the heat generated by the RTGs was reflecting off the back of the spacecraft's main dish antenna, gently nudging it forward, or, from Earth's perspective, slowing its retreat. In 2012, detailed thermal analyses using archival telemetry data strongly supported this explanation, showing that the observed deceleration matched what would be expected from this subtle thermal effect. So, was the Pioneer anomaly ever really a mystery? Yes and no. For years, it puzzled some of the best minds in physics, and it sparked fascinating debates about the nature of gravity in space. But in the end, the most likely answer came not from new forces or revised physics, but from old-fashioned heat, an engineering detail overlooked at first because it seemed so minor. But perhaps that's the real lesson. The Pioneer anomaly reminds us that the universe doesn't always need to be rewritten when we see something unexpected. Sometimes the answers lie in the interplay between physics, engineering, and incredibly precise measurement. And sometimes the smallest mysteries lead us to appreciate the incredible complexity of exploring space, not just out there, but also in the design of the machines we send Could future missions uncover new, genuinely unexplainable deviations? True clues to physics beyond Einstein and Newton? Perhaps. But the Pioneer Anomaly serves as a humble yet elegant example of how deep curiosity, patient analysis, and a willingness to question everything, even heat, can resolve one of space exploration's most curious puzzles. The Pioneer Anomaly refers to the unexpected small acceleration directed toward the Sun that was observed in the trajectories of the Pioneer 10 and Pioneer 11 spacecraft. This acceleration, on the order of 8.74 x 10m/s2, appeared consistently over long periods and across vast distances in the outer solar system. Initially, it puzzled scientists because it could not be fully accounted for by known gravitational forces or standard physics. As a result, the anomaly spurred extensive investigations into potential causes, ranging from mundane spacecraft systematics to new physics. Detailed tracking of the Pioneer spacecraft showed a persistent sunward acceleration that could not be explained by gravitational perturbations from known celestial bodies. It's like noticing that a car on a long highway subtly drifts to one side, even though there's no wind or road curvature to explain it. The anomaly is defined by a constant, small acceleration that appears to defy standard expectations from Newtonian gravity and general relativity. It emerged from precise Doppler tracking of the spacecraft's radio signals, which revealed a discrepancy between the expected and observed trajectories. This effect was particularly notable in the deep space environment, far from the influence of major planetary bodies. Researchers have since attempted to pinpoint its origin by examining both external forces and onboard factors. The Pioneer 10 and 11 missions, when analyzed with high-precision Doppler data, showed an unaccounted-for deceleration that persisted throughout their missions. It's like watching a ball roll on a perfectly flat surface and noticing a slight, unexplained resistance slowing it down, even though no friction or slope is apparent. One of the leading explanations for the Pioneer anomaly is the thermal recoil force, which results from the anisotropic emission of heat from the spacecraft. As the Pioneer spacecraft generated heat from their power sources, the uneven emission of infrared radiation produced a small but continuous thrust. This thermal recoil can account for a significant portion of the observed acceleration when modeled accurately. Extensive analyses of the spacecraft's design and thermal properties have lent support to this explanation. Detailed thermal modeling of the Pioneer spacecraft showed that the heat radiated asymmetrically from the onboard power systems could produce a sunward acceleration matching the measured anomaly. It's like a person in a boat using a heater. If the heat is released unevenly, it can cause the boat to slowly drift in one direction. In addition to thermal forces, researchers have investigated other non-gravitational forces that could affect the spacecraft, including gas leaks, outgassing, and solar radiation pressure. These forces are typically small and vary over time, but in the case of the Pioneer spacecraft, they were scrutinized as potential contributors to the anomaly. Systematic errors in tracking or onboard instrumentation were also considered. Ultimately, while these factors may have contributed, they did not fully account for the magnitude and consistency of the observed acceleration. Exhaust analysis and detailed inspections of the Pioneer spacecraft systems have ruled out significant contributions from fuel leaks or outgassing as the primary cause of the anomaly. It's like examining a car to determine why it's veering slightly off course, checking for leaking fluids or misaligned tires, but finding that none of these issues explain the subtle drift entirely. Mathematical models and advanced data analysis techniques played a crucial role in quantifying the Pioneer anomaly and testing various hypotheses. Researchers employed complex simulations that incorporated spacecraft geometry, heat distribution, and external forces to predict the net acceleration. The analysis of decades-long Doppler tracking data provided a high-precision benchmark for these models. This rigorous approach allowed scientists to gradually narrow down the likely causes of the anomaly. By applying sophisticated computational models to the Pioneer Doppler data, scientists were able to simulate the thermal recoil effects and demonstrate their consistency with the measured acceleration. It's like using a computer simulation to recreate the drift of a paper boat in a stream, confirming that the uneven current is the reason it veers off its expected path. Initially, the Pioneer Anomaly prompted speculation about possible modifications to gravitational theory or hints of new physics beyond the standard model. If the anomaly could not be explained by conventional forces, it might have indicated a need to revise our understanding of gravity on interplanetary scales. However, as the thermal recoil explanation gained credibility, the need for new physics diminished. Nonetheless, the anomaly has deepened our understanding of how subtle forces can influence spacecraft trajectories and challenge scientists to refine measurement techniques. The resolution of the Pioneer Anomaly through thermal modeling has reinforced the validity of general relativity while also highlighting the importance of accounting for all minor forces in deep space navigation. It's like finding that a mysterious wobble in a spinning top is due to a slight imbalance in weight rather than a new, unknown force acting on it. The pursuit of an explanation for the Pioneer Anomaly has spurred technological advances in spacecraft design, tracking, and data analysis. Improved thermal modeling techniques and more precise Doppler tracking systems have emerged as a result of this research. These advancements benefit not only deep space missions but also broader applications in engineering and navigation. The anomaly thus serves as a catalyst for innovation in the field of aerospace engineering. The insights gained from analyzing the Pioneer Anomaly have informed the design of subsequent spacecraft with better thermal control and more accurate trajectory prediction capabilities. It's like discovering a small flaw in an airplane's design that, once corrected, leads to more efficient and reliable flight performance across the entire industry. The investigation into the Pioneer Anomaly exemplifies the scientific method in action, proposing hypotheses, conducting experiments and simulations, and refining theories based on observational evidence. It underscores the importance of considering even small, seemingly insignificant forces in high-precision measurements. This case also highlights how long-term data collection and rigorous analysis can resolve seemingly perplexing phenomena. The comprehensive study of the Pioneer spacecraft's thermal properties and trajectory data set a new standard for evaluating non-gravitational forces in space missions. It's like solving a complex puzzle by carefully examining every piece and ensuring that even the tiniest detail fits perfectly into the overall picture. Future research will continue to refine our understanding of the Pioneer Anomaly and similar phenomena by leveraging new data from advanced deep space missions. Ongoing studies aim to further improve thermal modeling and develop more sensitive tracking technologies, enhancing our ability to detect and compensate for subtle forces in space. The lessons learned from Pioneer will inform the design of next-generation spacecraft and navigation systems. Ultimately, while the anomaly may now be largely explained by conventional physics, it has opened new avenues for research and technological innovation in space exploration. Upcoming missions equipped with cutting-edge sensors and thermal control systems are expected to provide even more detailed data, further validating and extending our understanding of minor non-gravitational effects in space. It's like upgrading from a magnifying glass to an electron microscope. Each technological improvement reveals new layers of detail that enhance our overall understanding of a complex system.